Hi everyone, welcome back to today's video, and in this video we will be talking about various types of selection bias. So there can be various types of selection bias like sampling bias, attrition bias, Bergson bias, Neyman bias, length time or lead time bias. So we will be discussing them one by one, and by the end of this video you will have a fairly good idea that what are these types of selection bias. So what itself is a bias? So, bias is a systematic error in a study that distorts the true relationship between the exposure and the outcome. So, I have underlined systematic because it is not a random or a non accidental error. If it is a random or an accidental error, purely due to chance or purely due to luck, that is called alpha error. We have discussed that in our video about alpha and beta errors. But bias is a systematic error due to some problem, due to some inherent problem in the study design or sampling. We know the reason, it is not random. Okay, so it is a systemic error in the study that shows a true relationship between the exposure and outcome, or we can say that it is a built-in flaw. We know the reason of it, but we don't know the reason of alpha error. It is purely due to chance. So various types of can bias can be of various types like selection bias, information bias, performance bias, detection bias, reporting bias, or confounding bias. So we will discuss all these bias in some other video, but in this video we will concentrate on selection bias because that is the most important bias that comes in the exam, and I think it is pretty important. So selection bias happens when the participants included in the study are not representative of the target population. So whenever you do a study, you enroll certain patients and you want that these patients should represent the real world population so that your results can be applied to the real world. But if that doesn't happen, then your study will not be much useful. You cannot apply the results to the general population. And selection bias, what it does is the participants included in the study will not be representative of target population. So we should try to minimize this selection bias. This can be due to several reasons. This can be due to wrong sampling, the study designs, or the way you recruit the participants. So, like you don't do the randomization properly, you don't do the allocation concealment properly. All these things. So this can lead to selection bias. It affects the internal and external validity of the study. So, what do we mean by internal validity of the study? The result of the study themselves, by themselves, are they valid or not? Is your p-value okay or not? Is your confidence interval okay or not? So that is the internal or the statistical significance of the study that you are getting. That is the internal validity of the study. So selection bias will affect the internal validity of the study as well as the external validity of the study. What is the external validity of the study? How uh, how successfully you can apply the results of your study to the population. So external validity means how successfully you can apply your results of the study to the general population. So that is external validity. Selection bias affects both internal as well as external validity. So sampling bias, it is a kind of selection bias, but it only affects external validity. So what do we mean by sampling bias? Sampling bias means that how you have recruited the patient, how you have taken the sample of the population in your study. So how that population sample is collected. If it is a problem, that means there is a sampling bias. So there can be several types of sampling bias. We will again discuss them in a separate video, otherwise it will be too complicated. So this is a cartoon here. If you see, there are 99% people says that I love responding to surveys, but only 0.2% of the people say that I toss them in the bin. Why? Because all the people who love tossing the surveys in the bin will not respond in themselves. So is this representative of a population? Is this the correct data? No, because our way of sampling the population is not correct. So this is the example of a sampling bias. We received 500 responses and found that people love responding to surveys. Is this a correct interpretation? No. So this is sampling bias. So what is sampling bias again? A systematic error in the data collection that occurs when some members of the population are systematically more likely to be selected for a study than the others. So you can understand from this diagram. I hope sampling bias is clear. One thing you want to remember is that sampling bias is a kind of selection bias, but it only affects external validity of the study. What is external validity? You cannot apply the results of your study to the general population. But selection bias itself affect both internal and external validity of the study. Attrition bias. Attrition bias happens when the participants drop out of the study and the people who leave are different from those who stay. This can distort the result. So see here, this is a population that you are studying. You progress with your study and some people leave in between with a common characteristic. So people who left are all blue. So if you go to the end of the study, are there many blue people? No, because blue people have left the study more. So this is attrition bias. Now your population is not balanced. The population you are getting at the end of the study will not be balanced in terms of this blue characteristic. So that is attrition bias, the selective dropout of participants who systematically differ from those who remain in the study. So suppose there is a weight loss study that starts with 200 people. After 6 months, 60 people quit. And these 60 people quit because they were not losing much weight. Now 140 people will say, oh, there is amazing weight loss. But these 60 people who are not here anymore to report the result that we didn't lose much weight have left the study. So our interpretation of the study will be that drug is very effective for weight loss or intervention is very effective for weight loss. Is that the correct result? No, this is not the correct result. So that is what is attrition bias. Attrition bias. Final study group no longer represent the original group. Now the question comes, if there is lot of attrition in the study, will you take the data? Just think about it. Yes, we will take the data for the patients who have lost to follow up or who has undergone attrition, like who are no more in the study. So we want to take the data of these 60 people along with the 140 people so that we can get the correct interpretation. So if the question comes, this is a high point, that if the question comes that there is 60% attrition in the study, so will you consider the data of this 60% people? Then the answer is yes, we will consider the data during the final analysis. So this is attrition bias. Attrition bias happens when the participants drop out of the study and people who leave are different from those who stay. This can distort the result. Although attrition affects the sample, but only at the later stages, not at the initial ones. That is why it is different from sampling bias. So in sampling bias, at the start of the study, we are doing the wrong sampling. We are doing the wrong sampling. That is why there was bias initially. At the start of the study, we were not taking correct people to start with. But attrition happened during the study, in the middle of the study somewhere. So that is why attrition is a kind of selection bias, not a sampling this thing. Sampling bias. It is not a type of sampling bias, but sometimes it is considered a type of sampling bias as well because it affects the external validity and also affects the sample at the final stages of the study. So you might ask that I am saying both the things together. So actually it is not a sampling bias, the reason I have told you, but sometimes there are some questions which consider it as a sampling bias. So if you don't find any choice appropriately, like you can keep this in mind that sometimes it is considered a sampling bias, although it is a kind of selection bias. Bergsonian bias, Bergson bias, sorry, happens when you study the hospital patients and try to generalize the results to the general population. But the hospital patients are not representative. So that is called Bergson bias. So if you study the association of stroke with pneumonia in a hospital, you will find an association. But is there a association of stroke with pneumonia? No. But then why will you find an association? So just visualize a patient who is lying in a hospital and he or she was admitted due to stroke. Now, are there chances that he can get ventilator associated pneumonia? Yes. Are there chances that he can get pneumonia, hospital induced pneumonia? Yes. Is it possible that he can get aspirational pneumonia? Yes. But is it related to stroke? No. It is only related to hospitalization. So in a hospital setting, there can be lot of association that you can find which are actually not there. And this is called Bergsonian bias. I hope this is clear. Okay. So happens when you study hospital patients, and you will find lot of association which are not actually there. So Bergsonian bias, you will always see if the patient is hospitalized, if they are talking about hospitalized patient. Now we will discuss Neyman bias. Neyman bias is a kind of survivorship bias or survivor bias. So let me tell you what is survivor bias. I tell you a story from a world war. So what happened in the World War II or World War One? I don't remember. When the planes came back, they have certain bullets here and there, right? They were hit with the bullets or like by missiles or whatever. So all the people thought that we need heavier armor. We need to protect this airplane where they are getting hit most, like this area, this area, this area. They want to protect their planes at these areas more. But a statistician came and said that perhaps they get it evenly and the planes hit in the most vulnerable parts don't tend to return. So what he is saying that this plane has come back and it is hit here, 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 here and here. So that means these are the strongest part, because after getting hit in these parts, the plane still survived and came back. But other planes who were shot in other places like here, 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 where there are no bullet marks, those planes got crashed. So we need armor at these places where there are no bullets. So what is happening here? There is a tendency to favor the survivors. I give you another example. So if you ask a YouTuber that what is the mantra behind your success, if you ask a successful YouTuber, he will say just consistently upload the content and you will get successful. But tell me, those who upload consistently, like every day, do they get successful? Each and every one of them? No. But still, we believe that you're a successful YouTuber because he's a survivor. So we have an inherent survivor bias, and that works in business and that works in philosophy everywhere. So Neyman bias is a specific type of survival bias that occurs in case control or cross-sectional study. So when we talk about survivorship bias or survivor bias in the context of epidemiology, in case control study or cross-sectional study, that is called Neyman bias. When the prevalence of disease is estimated based on the available surviving cases in a population rather than actual incidence over a period of time. This is especially relevant if the risk factor being studied affect both the disease incident and the likelihood of survival. So if there is a risk factor which affects the incidence of the disease but also the likelihood of survival, then this survivor bias or Neyman bias comes in. I give you an example. So a study on the link between smoking and COPD might find a lower prevalence of smoking among patients with disease than expected, because smokers with COPD may die sooner and are therefore less likely to be the part of prevalent group of survivors among being studied. So you find a population where there is lot of smoking but there is no COPD, or there are no cases of lung cancer. What does that mean? That everybody is dying because of smoking. But a new person who doesn't know that there is a association between smoking and lung cancer, he might think smoking doesn't cause lung cancer because there are so many smokers, but hardly there are any COPD patients. He might think that smoking is protective for COPDs or lung cancer, but that is not the case. The problem here is that COPD patient or lung cancer patients are dying more quickly because of the smoking. Another example, in a cross-sectional study, a risk factor may appear to be negatively associated with the disease simply because that the risk factor also increases mortality, causing those with the risk factor to be underrepresented in the survival sample. Same thing. So that is an example of Neyman bias or a survivorship bias in epidemiology. Neyman bias happens when a study misses people who died early or recovered quickly from the disease because they are not included, because they died or just recovered, and the results become misleading. It is a kind of survivor bias or a cognitive bias where we optimistically look at survivors, only ignoring the non-survivors. So basically, if it has become too complicated, let me explain it to you again. Neyman bias happens because we are only looking at survivors. So, in case of smoking and lung cancer, our favorite example, if we see a population where there are hardly any lung cancer, but there are lots and lots of chain smokers, it means that all the smokers, like lot of smokers, are dying because of lung cancer. So we cannot see lung cancer patient in that population. That is Neyman bias. I hope this is clear. So again, Neyman bias primarily used in epidemiology and medical research, especially case control and cross-sectional study, while survivorship bias is a broad term, broad cognitive bias applicable to many fields including business, investing, history, and military analysis. So Neyman bias is a kind of survivorship bias. Length time bias. So length time bias happen in case of slow growing disease. As the disease itself is slow growing, that means the screening test has a large window to detect the disease. I show you an example. So this is a slow growing disease. This is a fast growing disease. Now see here, symptom develops at this point. Here, symptoms develop at this point. Okay, between the green and red. The point between green and red in both cases. Now, a screening test can detect the disease only at this point in the green part. So if you look closely, our screening test has a larger window to detect the disease in the slow growing disease. This green is larger in length. This is smaller in length. So our screening test has lot of time to detect the disease if the disease is slow growing. So you will have more chances to detect the disease by screening test in slow growing disease, and you detect lot of patient with the disease by using a screening test. Now, what will happen because it is a slow growing disease, nothing to do with the screening test, nothing to do with detection. Just because this disease is slow growing and we catch more patients uh, with the screening test, we will think that screening improves survival because these patients will live more. Why they will live more? Because this disease is slow growing and these patients will die faster. And we are getting more positive result with screening in a slow growing disease because of the larger window. So larger window before the symptom develop, more positive screening test, more uh, larger lifespan. What is the result? That positive screening test improves survival. This is not the case. What is improving survival? The slow growing nature of the disease. So this is called length time bias. So length time bias happen in case of slow growing diseases as the disease itself is slow growing. Disease is slow growing. That's why people are living longer. Disease itself is slow growing means that screening test has large window to detect the disease. This large window before the symptom develops compared to this. So screening test has a larger window. Screening test has large window to detect the disease. If the disease is fast growing, then the patients may die before the disease is identified by screening. So see here, smaller window. Screening test will not have much chance, will not have much time to detect the disease. And before screening test detect the disease, patient will die. Small, small natural course. So this gives a false impression that the patient whose disease got identified by the screening procedure are living longer than those who didn't. This should be R. Sorry for the typo. But in reality, patients with slow growing disease are living longer than fast growing disease. Reality is these patients are living longer as such because this is a slow growing disease. These patients are dying younger because this is a fast growing disease. But we think that screening is detecting the disease, that's why they are living longer. This is the length time bias. And why screening is detecting this window. I hope this is clear. So you might think that here we are talking about survival, that these patients are living longer. So what is the difference between Neyman bias, which is a type of survivorship bias? So what is the difference between length time bias and Neyman bias in that case? So the difference is length time bias is relevant in screening studies. Neyman bias is relevant in cross-sectional or case control studies. People with high mortality or severity are less available for selection into the study. So you are doing a cross-sectional or a case control study, but patients with high mortality or severity will not be able to participate in the study. They want to be at their home and don't want any disturbance with high severity or high mortality. That is why Neyman bias is there. You will only see survivors. So you will get the data from the survivors only. You will not get the data from high mortality people or people with high severity of the disease. In case of length time bias, occur because test catch slow progressing disease much more than a fast growing disease because they have screening test has a much larger window to catch. Fast growing disease develops symptoms before screening catches them. So screening procedures don't have much chance in case of fast growing disease because before you detect the disease, asymptomatic patient, screening is done in asymptomatic patient. Before you detect the disease, fast growing disease will develop the symptoms. So there is no point in screening. You can make the diagnosis. Neyman bias can lead to the underestimation or overestimation of the association between exposure and disease. So we make association between exposure and disease in cross-sectional case control and cohort studies. If you have not seen my video on these studies, it is called epidemiological studies. So just go and check that video. And I have described the cross-sectional case control and cohort study in detail in that video. So that is Neyman bias. Length time bias leads to the overestimation of survival benefit of a screening program. When it is not effective, you may think that it is effective. As the detected cases inherently have a better prognosis than the missed aggressive cases. Pretty clear, we have discussed this. Lead time bias. Now remember, length time bias depends on the fast growing disease or the slow, whether the disease is fast growing or slow growing. Lead time bias does not depend on that. Lead time bias is very simple. It occurs when patient diagnosed earlier appear to live longer because they know they have the disease for longer. So, if this is a disease, this is a survival time, and symptoms develop here. So, if you do a screening and you make a diagnosis here, patient might think that I have lived so long after the screening procedure. So, screening procedure might have increased my survival period, but this is not the case. Patient died at the same time. So, suppose this is 60 years of age in both the cases. This is 40 years of age when the symptoms appeared, and this is 20 years of age. So now, if you screen the patient at 20 years and he lived till 60 years, he might think that, oh, after detection, I lived for 40 years. Let me do this 20 years, 40 years, 60 years. So, if screening happens at these 20 years, patient might think that I have lived for 40 years after the screening procedure which detected my disease. But if he doesn't undergo screening, and he develops symptoms at 40 years and die at 60 years, he might think, oh, I only survived for 20 years without the screening procedure. So this is lead time bias. It occurs when patient diagnosed earlier due to a screening method. You have done the screening and patient was diagnosed earlier, appear to live longer because they know they have the disease for longer. So I hope this is clear. If not, I will explain one more time. So suppose here you have done the screening. At the age of screening, patient was 20 years old. Symptoms develop at 40 years old and patient died at 60 years. Now if you have done the screening at 20 years and you diagnose the disease with a screening procedure, patient will live for 40 years and he will think that I have lived for 40 years after the diagnosis was made by screening. But if you would not have done the screening, he would have got to know about his disease at 40 years because symptoms are developing at 40 years. So he will think that I have lived only for 20 years. So there is an illusion that I am living longer because of the screening. So that is called lead time bias. I hope this is clear. So lead time bias, it is a form of a systematic error that makes it appear as though the patient diagnosed earlier lived longer, even if the treatment or screening has no real effect on the natural course of the disease or the actual time of death. This occurs because survival time is measured from the point of diagnosis, and earlier detection simply shifts the starting point forward in time. Hope this is clear. So this is from my end. I will cover the sampling bias and other types of bias in a different video. And if you have liked my video, please like, share and subscribe. And I will see you in the next video. Thank you.